In this lecture, we're going to look at the way atoms bond. Some of this information may be review, but hopefully most of it is new. First of all, we might ask, why do atoms even bond? And the reason they do is because most elements in nature are going to be unstable, and it's related to the number of valence electrons. And I have a little periodic table here. Just a reminder, you can look at the column number, and that tells you how many valence electrons, just counting left to right, how many valence electrons. Well, it turns out that we want 8 valence electrons. That is what makes an element stable. That's considered a full outer shell. And it's when we have a full S, because that's 2 electrons, and a full P, which is 6. So if the sublevel SP, so a 2S, 2P, 3S, 3P, if those are filled, it has the 8 valence electrons. And it's also called the octet rule. Helium's going to be the only exception because it only needs to fill the 1s, so you know it only needs 2 electrons, and then it would be stable. And then bonding does occur between valence electrons, those outermost, the ones in the highest energy. The 3 types of bonding that we'll look at are molecular, which is sometimes called covalent, ionic, and metallic. We've already looked at formula writing for ionic, but we're just going to look a little bit more at the bonding. Types of elements, molecular are going to be made out of non-metal only. Ionic is with a metal, or it can be the ammonium ion, that would be most common if it's not a metal, plus a non-metal, so metal with non-metal. And metallic is usually made of many atoms of the same metal element. Molecular bonds form by sharing valence electrons. The element that is more electronegative will pull the shared electrons closer to itself. So here we see a bonding between oxygen and hydrogen, and it's actually slightly closer towards the oxygen because it is more electronegative. In ionic bonds, we know neutral atoms are going to exchange, transfer. Sometimes we say steal valence electrons, and then they become ions. So the bond is formed between the attraction between positive and negative. Remember that metals tend to lose valence electrons, and that makes them cations, while nonmetals are going to gain valence electrons and become anions with a negative charge. Metals use metallic bonding, and we'll see more about that in the next slides. Metallic bonding actually is really kind of interesting. We have lots of closely packed metal atoms, and their valence electron orbitals overlap so that the valence electrons can jump from one atom to another. And we see that here in this image. Here's an electron jumping over to this atom. This one curves around and jumps over here. One here jumps up here. So we have these electrons that are actually able to jump all around with these overlapping orbitals. The jumping valence electrons means that they're not held to one particular atom, so they're not locked in place, or we would say they're not anchored in any one place. The moving electrons are called delocalized electrons. Make sure you know that term. And again, we have another image here. You can see these metal cations, and then notice we don't have nice, neat electrons around them. Some of them we see a lot more electrons around them, and some we might only see one, or it almost seems like there's almost nothing here. It just has a little one there. Metallic bonding then forms when a group of metal atoms of the same element share what's often called a sea of valence electrons. And we can see that here, all of the blue is different valence electrons that shows arrows for the movement, and then we've got those metal cations from the very closely packed atom. So some special properties that we get because of metallic bonding is conductivity. Conductivity is the ability to conduct electricity. In order for that to happen, you need to have some charged particle, and we get that because of those electrons. They are charged, and because they're moving around from one area to another, they can create a current, and so it allows for electrical current to flow. Metals are then considered good conductors. Two other properties, malleability. which is being able to pound the metal into sheets, pound into thin sheets, is malleability. And then ductility is being able to pull the metal into thin wires. So sheets versus wires. And the reason, again, that we can do all of this pounding and pulling with the metal is there isn't a specific bond between two atoms like there is with ionic and molecular. We just have this lump of atoms with the sea of electrons. And so the atoms can actually kind of slide around and be pushed. And here it shows different layers. We can see 3 layers here that can slide over one another. And in this image, a hammer comes in, hits this one, and it pushes it up into this space here so that now it's located up here in this second row. And so that's what essentially is what's happening with malleability and ductility, this sliding and moving of the atoms to rearrange the shape. Lastly, we get luster, which is like a shininess. And those delocalized electrons are going to move easily between different energy levels. We saw in an earlier unit about electrons jumping to higher energy levels and they drop back down. So they jump up, excitation, relaxation, dropping back down, and we know that's when they give off those wavelengths. And so because we have so much movement, there are many wavelengths of light that are being absorbed, released. Released is the part we see. And so then it's seen as gleaming white, glinting white gleam, which we call luster. And that's it for this lecture.